Okay, so in this live stream, we're working on a visualization of like small neural nets on grids of points in R2, and we're trying to look at the idea of using a image classifier to generate images by backpropagating to pixels. And we're kind of coming to the empirically that doesn't seem to work. Like you can backpropagate to pixels to find images that highly activate a neural net output, but the resulting images do not look like images. And so we're trying to understand why. And so we're taking like this kind of interpretation of a small two-dimensional neural net as like a series of like geometric deformations of the input space. So the basic idea would be something like maybe this guy and this guy are like positive examples for the classifier. But when like after the neural net has deformed the input space, you have like those points maybe are over here. And so you have like a lot of like incidental points that are brought with the positive example points. And so we're just trying to see if you can say anything about what we're calling like incidental points in relation to the like training examples. And also like if it's possible to like further filter away like incidental examples. I mean, if you think about it, it seems like like there's gonna be like an exponential number of like incidentals because Rn is like dense. But yeah, I mean, like it's like okay, so if you have one positive example point, and like the neural net successfully classifies that point, meaning like it successfully moves it across the final hyperplane. Like how many points are brought with that training point? So that's kind of, I guess, just what we're trying to develop like visual intuition for. And so I think the first thing we're going to do is like what we have here is the network training. So like the points are moving around. And I think first of all we're going to disable training and then just like look at the types of like geometric transformations that like a single that like a random neural net sort of induces on the space. So the idea is like these points, like this point here is mapped to this point, like they're color mapped. So like these dark blue points are over here, right? So like this currently is implementing some sort of, I guess like reflection or more like a rotation, like it's rotating at 90 degrees. Okay, so we'll look at some of that, and like for multiple layers. So the neural net right now is 0 hidden layers. No, that's not true. It's 1 hidden layer. So it's just the neural net right now is you have 2 inputs, and then you have these 2 hidden layers, hidden layer units, and then you have 1 output, and like we're not visualizing the output, so that's more or less pointless right now. And so we're going to disable training and then just like look at random neural nets. So I believe this disables training. Okay, so yeah, so there you go. That is a one hidden layer. So it's like the very first layer, it's, you know, mapping these guys over here and mapping these guys up here. It's like, I wonder if I should like draw lines between the points. Like, that may or may not be cool. Okay, so we're getting like weird circular. I mean, like, also, by the way, if we take out the nonlinearity, then, you know, like the tan H here, then like we're literally just computing like random linear combinations of, you know, I mean, it's like a linear transform. So if I make the activation linear, then yeah, like these are random linear transforms. So like the effect of the nonlinearity kind of appears to be to make things more circular. It's also kind of an observation is that it seems to be like the average effect is to like shrink the, right, because like these areas in the activation space are never going to be activated because like these are all possible inputs. I mean, we're literally in R2 and it's like each, you know, -1, +1 on both dimensions. So it's kind of interesting that like, I guess in like a random linear transform, you have huge amounts of like the possible activation space that is not, will never be used. So it seems to be like a random linear transform has a like compressing effect. Although that also probably depends on the initialization of the weights, which I don't even know what the initialization is. It's whatever the default TFJS initialization is. Okay, so then we're using a nonlinearity, so you get things more circular. Okay, so let's add another layer. So it's going to be visualized right here. But like, you know, I mean, like there's kind of this idea that like a single layer, like in terms of separating, right? Because like the neighbor relations are basically preserved. So there kind of seems like there's a question of like, okay, what is like the computational like separability power of like a single layer. But okay, so let's do 2 layers and visualize 2 layers. So I need to get layer 1, layer 2. So I assume that's the output, and then we need to draw it. Yeah, okay, so you just need to draw it. And the canvas already exists. Whoa. And there's probably a smarter way of having to change all the individual things here. Okay, so that's L2 outs, and then we're drawing on canvas 2. There's gotta be like a better way of doing this. Canvas, okay, that's fine. Okay, I think that's everything. Okay, so we should have like 3 canvases. There you go. Okay. That's weird. Like it, you know, I mean, it definitely seems to be like the general trend is like geometrically compressing the activation area. But also, like, clearly, you know, like, it's very much preserving, like, neighbor relationships. You know, like, if your neighbor's over here, you're going to be very closely matched. Okay, so we have to do the obvious thing, which is one more layer. For which I will have to add another canvas. So that's kind of annoying. Okay, so canvas 3. I wonder if I should make them smaller. Append canvas 3, canvas 3, 3, 3, 3. Okay. Right? And then, okay, and then add another layer. And that will be layer 2. And then draw. So, oh my god, this takes so much work. I guess it's like L3, 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 G3, 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 G3. Okay, I think we're good, right? Maybe? Let's find out. Okay. I do wonder, like, how much this depends on the initialization, or the weight initialization. I forget, like, yeah, like, what if you do uniform? But anyway, I mean, like, I think a thing that's clearly obvious is, like, the, you know, like, the grid structure, like, the neighbor structure of the input space is mostly being preserved through random deformations. Okay, so I think we're gonna go back to actually training, and the thing I need to do is implement, because we need to specify positive and negative examples, because we're doing, like, it's just a binary classification. And so yeah, so we have, like, the grid, and so we then just, like, select indices into the grid, and then we say whether they should be classified positive or negative. And so we need to visualize those indices. So I think I need to pull that out, and I think I need to say, like positive indices, negative indices, and yeah. Alright, so I guess for now we won't have negative indices. So like we're indexing into the grid, like the points in the grid. So I think it's like, so like this would be point 0, 1, 2, 3. I think, like, assuming that's how it works. And so given the index, I need to visually demarcate it, which I think I will do just by putting a square around it. And then I need like the square to continue for all the layers, because we are going to be updating the weights. Okay, so so we'll say like positive index 50, or so that's like my one positive example. So all we're saying is that we want the neural net to classify point 50 as a positive example, and I need to okay, so the first thing I need to do is visually distinguish point 50. So I'm going to put this up here. So this is training set. And then we need to visualize. So I think, yeah, I think it's going to be easy. You just say like, yeah, actually you need to enumerate the grid points. Well, that's annoying. Okay, so let xy equals grid points I, and then I is less than grid point dot length I plus equals 1. Okay, that should all be good. And then it's like, if I is in the positive examples, we'll just do a linear scan of that. I don't know how you express that in JavaScript actually. How do you say whether an array contains an index? I don't know. Indices dot contains? Okay, I'm just gonna Google that real fast. Maybe. It appears that this crashed. Oh, yeah, that's fine. Okay, so JavaScript array contain elements includes. Cool. You gotta know the lingo. Okay, includes I, and then it's like, if it does, then draw a square. Yeah, how do you stroke a square? Like, stroke rectangle. Perfect. Also, the stroke style needs to be, I guess, like green, so it's a positive example. So this is 0, this is 255, this is 0, okay, so stroke a rectangle at the location of the point, so like here, And it needs to be, I mean, big enough. Like, I mean, it has a radius of 10. So yeah, so I guess it would have to be 10 by 10. Okay, let's see if that works. Well, it drew a rectangle, but, oh, I see. Okay, so we're gonna have to, you have to offset it. That's annoying. That is the correct radius, though. So you have to offset it by the radius, and then double the size. I can do that. Okay, so like offset by, okay, so the radius is 10. So this minus 10 pixels minus 10 pixels, and then double the size. Okay, perfect. And then, so if I had like another one, if I say 11, that's weird. Oh, okay, so like it's indexing from here. So this is like 0, 1, 2, 3, 4, 5, 6, 7. Oh no, it's indexing from here. Oh, it's going down the columns. Okay. That's fine. Okay, so I just need to continue that to all the other canvases, which I don't think is too hard. Because this needs to be X and Y. Okay, G2, G2, and G3, G3. Okay, so now we should have rectangles on all of the images. And we do. I mean, like they're being overwritten by subsequent thingies. Okay, so now we're going to go back into training. So, like, if these are positive examples, like what has to happen is that the neural net has to make them linearly separable. Well, let's see. No, it doesn't have to make them linearly. I mean, it just has to put them on such that they're on one side of like an arbitrary hyperplane chosen by the output unit. So, yeah, I mean, I think, oh yeah, also it needs to be green though. Why are they not? Oh, because this needs to say stroke style. And, stroke style, does that work? Yes. Okay, so it needs to say stroke style. And up here it needs to say stroke style. Wow. Okay, great. Yeah, let's do negative examples also before we start training, because, well, no, okay, let's just run training. So the training is these two indices, we want to assign a 1, the classifier. And so that should work. I don't know what it's going to do, but I mean, yeah, so, like, it just has to put a hyperplane right here. I mean, basically it looks like it's assigning all of them a 1. I mean, I guess it's only interesting when you have like negative examples. Because, I mean, otherwise it literally doesn't matter. Yeah. Okay, so we'll do negative examples. Like, right, so like we'll try to separate 12 from 11. Is that possible? Don't know. Okay, how do you concatenate arrays? You can just use add, isn't it? I guess we'll find out. I mean, you can do that, right? No. Like, you can't do 1, 2, plus 3, 4? Oh, no. 1, 2, concat? Yeah, that makes it into a string. Okay, we want concat. My bad. Concat. Okay, and then we need to do the same for negative examples, except we want them to be highlighted with red. So that's annoying. Yeah. It's like if you had like GPT TP3 or whatever, like you can do natural language and it just does it. But yeah, we don't have that. So okay, so like G2. Oh no. G2. And hopefully this is the last one. G3. No, it's not. Where's my red square? I'm not seeing a red square. Oh, no, it is there. It's right there. I need to like make these thicker because I can't see them. Also, what the hell did it do? I mean, well, it did separate them. Look at that. So you have the two greens and then the red is down here. So you can just smack a hyperplane right between there and you're all golden. And then you have like, these are incidental points that the classifier chose to, right? I mean, like that's how generalization happens in a neural net. It's just like you have these points that come along for the ride or whatever, and then it just turns out to be that like if you're doing like image data, like the points that come along for the ride are like the correct points or something. So okay, so I need to make the I need stroke thickness to be larger. JavaScript canvas stroke thickness. How do you do that? Line width. Okay, cool. So it's just dot line width. So I have to go back and do line widths. Is it? Shouldn't it be like stroke? Yeah, I feel like it should be. I should just be able to put it in the style string. So like stroke style. Yeah, I should just be able to put it in the string, or no? Yeah, color. Okay, it doesn't look like you can. Okay, so whatever. So line width is 3. Is that gonna work? Can't tell. Yeah, I think. What, it was only on the 3rd canvas. Yeah, that looks better. Okay. Okay. Cool. See, it did it again. It separated the red from the green. And like it does it by putting like the entire input space on like a line, and then it just cuts the line in half. So that's weird. But okay, let me set all my line widths. Oh my god, I hate doing line width. Okay, I think that's it. I mean, I guess you should do G0. Yeah. Also, I think, I should probably, okay, yeah, like the red is hard to see, but it's like, see, it's like a weird problem because like these two are neighbors. And yeah, so to like linearly separate them, it's kind of like probably hard to do. So like if you're here, right, like the first layer, like there's still pretty much neighbors, right? So that's kind of the idea of like a single layer cannot do like a large amount of work. Although, like having said that, like these, you could linearly separate right here. So, also like the thing that like I really want to do is be able to use a mouse, you know, and just be like click, click, click positive and negative examples. Yeah, so, okay, so it's like, okay, here's one. Okay, this guy, I'm gonna make all of his neighbors negative examples. Although I don't know how to find his neighbors. What is this guy? This guy's like 50. What index is he? What is that index for that guy? That is 50. So, yeah, so we're gonna make, like, okay, so 49, 51, and, I think 40 and 60 are gonna be the neighbors, right? 49, whoops. 49, 51, 40, 60, and see, it's like I have to do this manually, like, which is probably, yeah. Well, yeah, no, I could, yeah, I think probably in the next stream, like, I'll automate that or something, or, because, okay, so, let's see what that does. Oh no. I didn't correctly get the neighbors there. Also, did it break? Like, what's happening? Okay. let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Oh, there needs to be a comma. Whoa. See, now this is cool. Oh, it doesn't look like it's gonna be able to do it. It can't do it perfectly. This is what I'm talking about, like a single layer of a neural net. Can't, like, I mean, you see what it's like? It's correctly separating these reds from this green, but it doesn't seem like it can break out the green being surrounded by the reds. Maybe, I mean, I don't know. I mean, it's still working. Like, I mean, like, gradient descent is, it never gives up, you know? It's like an inspiration to us all. Holy sh... I think it did it. Oh, it did it. Oh, it did it. It did it. What the hell? Okay, so it did it. Like, there's a green here. There's a green here. And these are the reds. Yeah, I'm going to need to make it so that the squares are drawn last. But like what is it doing? Like, how is this interpretable? Like, what is all this? Like, where are those even in the image? It's like purple to green. It's, what is it doing? Like, that's completely not interpretable. Okay, let me do one more thing where I make the squares drawn last, because otherwise they get overwritten, unfortunately. So, yeah, like, it took a while for... Oh, also, like, batch size. That just needs to be the total number. I'm just gonna make that like 20, because I don't think, or I don't know. Because I don't think I'm gonna have more than 16 points. Okay, so we need to do these last. So I think the only way to do that... Can I do them all at once, though? Well, I mean, you have to do it for each canvas. I think the only way to do it is just to loop twice. Because... Is there a way to do it without looping twice? Or... Oh, no, you can just... You just loop through the... Yeah, you loop through them separately. Okay, yeah, that makes more sense. Okay, so we're gonna modify this one more time. And we have to say for let index of positive indices, and then like draw it. What's going on here? So like let x, y equal grid points for the index, and then do this. This is like very annoying. Negative indices, and we want this to be 255 red. So so that should, oh my god, it didn't work. What's the matter? I is not defined at 137. Yeah. Oh, yeah, well we don't have this anymore, so oh no. Oh yeah, that worked. Okay, so we don't have that. Don't have that. Okay, cool. And then I just have to copy paste this for every single canvas. And change the canvas reference. Oh, and also delete it from the other canvas. Okay. So canvas 1, and then yeah, but then you have to say L1 out, isn't it? Yeah, I think L1 out. Is that cool? Oh no, because it has to be G1. G1. Is that cool? Yes, that is very cool. Okay, so I just have to do it for the other thingies, and then we're good. So this guy, I guess it's like G2. Oh no. Oh no. Like, I'm pretty sure there's a smarter way of changing all these. But I don't know how. Okay, then G3. Oh god. G3. G3. Okay, are we good now? Oh, something broke. Oh, because, yeah, this is L3 outs, so you have to use L3 outs. And that also has to be L3 outs. And up here has to be L2 outs. Okay, I think we're good. L1 outs. Right? Yeah. And then L1 outs. Okay, I think we're good now. Yeah, I think that works. Let's watch gradient descent, more specifically attograd with momentum. It's got to separate this guy, which is stuck over here, and it's stuck over here. I mean, it kind of seems like there should be, you know, positive, negative example patterns that a single layer can, like, never represent. I mean, that seems like obvious. But what about if you have, you know, like, I mean, here we have, like, 3 hidden layers. Is, like, 3 hidden layers, like, universal over, you know, all patterns of positive, negative examples? I don't know. Also, is it going to successfully separate this like last time or not? I also don't know. It's doing something. It's like, what are all these, I guess these are just like the rows. Right? It seems like its instinct is to put everything in a line. Now I don't know what's happening. Oh my god. It's vibrating. That's never a good sign. Yeah. It's like if your gradient descent is vibrating, that means it's broken. Okay, so well, it did it, right? You have green here, all the reds are here, and you can put a line right between them. Vavoom. Okay, so what about, yeah, we want to fix this where it's like actual, yeah, I think I'll fix this and then like in the stream. If I can fix this though, like what's, so this is 50, this is 49, this is 51. Why is this not, shouldn't that be 40? Or maybe it's like 39? Maybe it's 39. There's probably like some mathematical pattern there. Okay, where's the, okay, so we're gonna say that's 39. Is that 39? It is. Huh. Okay, so then the other one's 61. Alright, here we go. Here we go. Separate those guys. Good luck with that. Also, I wonder if I took away this guy, what that would do. But looks stuck. I mean, probably. Because, I mean, like, technically this arrangement gets everything correct. Like, you just put a hyperplane right here. It gets everything correct except for one green example. So it's probably a pretty good score. But, it's not good enough for gradient descent. Jeez. Like, what the heck just happened? I mean, what is that? Okay, so like it put it on an S, and now you can linearly separate. So this is like a perfect score, or like perfect error, whatever. And yeah, and then like we have the issue of like you know, so like if you were doing a thing where you're like, I'm gonna back prompt to pixels, I want to find an input point that like maximally activates like the positive classification. You know, like what you want is one of the green guys, but like what you're actually going to get, like in all probability, like is one of these like purple guys that are coming along with the green guys, which kind of makes sense. You know, it'd be cool if I had like a mouse over, like if I moused over this guy, then it would highlight it in every other canvas. That's a thing to think about. Anyway, we'll do this one more time, because, I mean, it is pretty cool to watch. It's like, it does it differently every time, you know? Yeah. Okay, so it has this guy separated. Good, good, good. I can't tell where it is over here. This is a green. I guess there's a green and 2 other reds. Oh no. Whoa. Wow. Oh, it did it. I think it did it. These are the 2 greens, and these are the reds, so you can linearly separate. So there you go. Like, that's how, like, a 3-layer, 2, 2, 2, 1 neural net, like, separates these types of classification tasks in R2. So, yeah, I'll probably do some more of this stuff later. So thanks for watching. And,